Hi everyone, my name is Kartik and my channel is about mental models. In this video I'm going to be talking about thermodynamics. Thermodynamics, like a few of my previous videos, comes from the world of physics. But don't worry, this video is not a physics lecture. It is explaining thermodynamics as a mental model. Thermodynamics is a useful intellectual framework. It helps us to make an educated guess about problems, scenarios, or issues. I must add that it may not get you to the absolute correct answer, and that is because, firstly, we shouldn't use this mental model in isolation, but as part of an interconnected way of thinking with other models, mental or otherwise. And secondly, mental models are not always perfect. Remember my previous videos on the map is not the territory and connecting mental models. The links to both videos are in the description below. But it will get you close, and as the saying goes, it is better to be approximately right than precisely wrong. For this mental model, we will use the first and second laws of thermodynamics, which are namely energy can neither be created nor destroyed but changes from one form to another. So energy can neither be created nor destroyed. And number two, the second law, is entropy increases over time in a system. So let's look at the first one with an example. I read about this example on the internet and it is such a vivid example, so I thought about reusing it here. And the example is in the form of a question, and the question is, why is there such a big difference in the size between an elephant and a blue whale? So if that's the blue whale, then your elephant is sort of approximately sort of this size. So that's your elephant. It's about the size of the tail. Now, this may seem like, I'm going to call this size. Now this may seem like a very random question, but there is more to it. The elephant is the largest land mammal and the blue whale is the largest water-based one. So my question is looking at comparing the sizes of the largest land and water-based mammal. Now that makes the question a little bit more connected and less random, and the question now seems more interesting, I'm sure. So there could be a number of reasons why there is such a disproportionate size difference, and those would need to be explored. But one of the reasons would be looking at this question from the angle of the first law of thermodynamics. From the definition, we know that energy can neither be created nor destroyed. It changes from one form to another. So where do mammals get their energy from? They get their energy from food, in a nutshell. And this will change into another form during metabolism. Metabolism is sort of the process of breaking down the food, and that will release energy. The energy will then be converted into movement or physical activity and heat. The reality is that a lot more heat will be produced, which will need to be released through the skin. Now, if we take a thought experiment, link to the video is in the description below, alongside this, if we take a thought experiment alongside this to say that the blue whale is 10 times the size of the elephant, So if this is 1x, then this is 10x. Now, I'm just making this number up because it's easy, but it might be a bit bigger. The blue whale might be more than 10 times, but it's just a round number. That's why I'm using this. So this will mean that volume-wise, the blue whale is 1,000 times bigger, and surface area-wise, it is 600 times bigger than the elephant. So the volume is, say, 1 times 1 times 1, and here it is 10 times 10 times 10. And the area here would be 6 times 1 squared, and here it would be 6 times 10 squared. So don't worry about the maths. The point I want to make is that the volume is in the thousands and the area, but the area is in the hundreds. That's the key point. So this is the important bit. Don't worry about the numbers. It's just that the volume is in the thousands, the area is in the hundreds, so the actual numbers don't matter. Now this means that the surface area, the skin, would be too small to dissipate the heat generated. If your volume is in the thousands and your area is only in the 600, is in the hundreds, in this case 600, it's going to be too small. If the difference between the heat produced from metabolism and the heat released from the skin, if that difference is too big, then that heat will stay in the mammal, and that will mean the core temperature will rise, and if the core temperature is too high, it could lead to death. And so heat loss is a hurdle based on the first law of thermodynamics. So that's a problem. Now, having said that, if you are water-based, then the rate of heat loss is higher. So let me say that again. If you are water-based, then the rate of heat loss is higher in water than air. And this is why when we, let's say, cook something like a sauce, so let's say we've got a sauce and we want to cool it down quickly, we put it in another bigger utensil with water around it, and sometimes we have ice cubes on the bottom as well, and that helps our sauce, which is steaming hot, to cool down quicker rather than if we just left it on the side in air. And it's the same principle here. The rate of heat loss in water is quicker, and so by putting the hot sauce in water, it cools it down quicker. And so taking this and going back to the elephant and blue whale, it would mean that the heat loss hurdle would be much lower for anything that is in water compared to anything that is just in air. In other words, the blue whale, which lives in water, will have a higher rate of heat loss than the elephant, and because of that, the blue whale can afford a lower or a lesser surface area to their volume. They can get away with this kind of ratio because they're in water, and because the elephant isn't, it can't get away from this hurdle. The hurdle is too high for the elephant to grow to that size because they just will not be able to dissipate the heat, and it could be fatal for them. So for their survival, they can't grow that big, but a blue whale can, and therefore blue whales can grow a lot bigger than elephants. So that's the first law. That's looking at this question from the first law of thermodynamics. And you might think, well, hang on, there's other elements, there's this, there's that. I'm sure there are, but I'm just trying to prove this point that there is this angle as well, which on the face of it doesn't seem overly absurd. Someone might say, well, what about dinosaurs? They were on land and they were huge, and what about them and how did they survive? They were reptiles, they weren't mammals. These are both mammals. Reptiles are cold-blooded, mammals are hot-blooded, and so there's the whole sort of heat loss angle, which is evident in mammals, but it's very different in reptiles. So that's the first law. Now, on to the second law with another example. Example 2. The second law is entropy increases over time. Now, I read a phrase on entropy a bit like where I read this. I read a phrase which I liked very much, and that is that entropy is the universe's tax on time. Simply put, it is that any time someone does some work, there is energy used in the non-productive elements, and that is akin to increasing the entropy. Now, if you remember my example from the friction and viscosity video recently, again, link is in the description below, I gave the example of sort of me trying to move my sofa. And in doing so, in this example, in doing so, part of my energy, or probably a lot of my energy, is sort of going to go or going to be used in dealing with the friction. And so that's an example of entropy. Another example is when we are heating up water. Let's say we've got a vessel, we've got some water in it, and we've got some, let's say that's just some fire. We're trying to heat it up. When doing so, a lot of fuel will be lost as heat to the surroundings, and some of it will be transferred. Let's use another colour. Some of it will be transferred into actually heating up the water. All of this is entropy. So entropy is a measure of disorder. This also means that if left alone, the universe tends towards chaos. And so it takes energy and effort to maintain order. A real world example is that if your bedroom is messy, you need to put in work and energy to clean it, or the next time you use it, the bedroom will only get messier. And so the key thing, there's a lot of information that I've given with the first law and the second law here. The key thing in this mental model is to be able to see that story of energy. It's to be able to see that story of energy. And this, if you can understand the story of energy in things, it can help explain things and get us to a solution and a positive outcome, which is what mental models is about. And it will give us, along that journey of trying to solve our problems, it will give us a better appreciation for the complexity and fragility of life and the universe and everything within it. So the key, these are all very isolated and random examples, you may think, but the key that brings it all together is to see the story of energy and see how we can use that to our benefit to solve the problems or answer the questions or scenarios or issues or whatever it is to get a positive outcome. Finally, as I said before, I keep on coming back to the first law, energy can neither be created nor destroyed. And so there's an element of interconnectedness between everything in the universe and life. And that is very similar to mental models, because mental models are interconnected in one way or another. And so there is this little sort of lovely relationship in the first law of thermodynamics and the concept or subject of mental models as a whole. And that's all for this video and for thermodynamics. I hope you liked this video. If you did, then please like, share and subscribe to my channel. And whilst you're here, please do check out some of my previous videos which I've mentioned in this video. They're all flashing on screen right now. And I will see you in the next video with another mental model. Thank you for watching. Bye bye.